Hello everyone. Thanks for coming. As Vicente said, I'm Byron Orjuela. I'm from Cali, Colombia, and based in Universidad del Valle. My supervisor is Cesar Alonso Valenzuela. In this work, the matter power spectrum from physics inspired machine learning is part of a work I'm doing with Domenico here. With Sabas series at Instituto de Física Teórica in Madrid. So, okay. The work it is now is about symbolic regression, and in this kind of in these kinds of problems, we want to find a relation between some parameters, variables, trying to fit a given data set. So in summary, this technique is a machine learning technique, unsupervised machine learning technique, in which we have two individuals, and indeed we have a set of individuals, which are just expressions, random expressions, and we want to perform some operations in this kind of expression. In particular, we want to do mutation, which is only a random change in a part of this expression, and crossover, which is just mix some parts of expressions. And with this technique, we want to fit a data set for a given relation. For example, we have here this f of x, this function, and this is just a simulation and how the genetic algorithm is performing. And this is the chi-square, which is just a measure of the fitness, the goodness of fit of the final expression. So you can see here that our function is well fitted by this expression here. Okay, so in the case of cosmology, we would like to have also analytical expressions for very important quantities like the matter power spectrum. And indeed, we wanted an expression for the transfer function, which encodes the scale dependency of the matter power spectrum. And then this is just a summary of what is the matter power spectrum. We have a Seldovich spectrum, which is given by k to the ns, where ns is the spectral index. And we have a constant, which depends on primordial physics, encoded in the primordial power spectrum. Okay, so for this transfer function for lambda CDN, indeed we have some formulations given by this old paper by Vadim, Bondi, Kaiser, and Salai, which found this transfer function considering cold dark matter invariance. And the problem with that formulation, which is prior to Boltzmann solvers, is that it's very simplistic for model requirements. So some 10 years later, we found the Eisenstein-Hu fitting formula, which indeed has a great performance, considering variance also and cold dark matter. And as you can see here, comparing with CMB-FAST, I remember well. This is the performance of that formula, the Eisenstein-Hu formula, and it is okay, but the current needs. But the problem is that it is too complicated to add, for example, to a code. So at the end, we need around 30 different expressions in the fully formalism of Eisenstein-Hu. And thus what we wanted is to use this genetic algorithm to find a simpler formula and yet more accurate. So at the end, we found this formulation you can see here, where X is encoding the amount of matter and baryons, and also the scale. And you can see here that the accuracy of our expression is around the similar to the Eisenstein formula, and much simpler, we also consider a simple extension of the lambda CDM model if we are considering massive neutrinos. And this is the performance of the formula, the average performance. It is the average over all the matter values of the matter, baryon, and neutrinos we consider. And in this case, we found a better formula in terms of accuracy than the Eisenstein hoop. And okay. And thus, we wanted to move to a harder problem, in this case, which is to consider general effects of modified gravity in the theory. So, in summary, we can in summary, we can say that the matter power spectrum, when modified gravity effects are taken into account, consider only three main effects. So the first effect is an overall enhancement or suppression of the total amplitude. And the second one is just a shift in the equality scale, mainly due to changes in the amount of matter. And the third one is a variation in the power spectrum at the larger scales. So is this shift here. So we try to implement these effects in a formula. And so we found this, that the variations in the amplitude at the larger scale is considered just a shift encoded in this parameter S. The overall enhancement or suppression of the amplitude takes also the matter transfer function we found earlier, which is this formula here. And the suppression is encoded in this alpha parameter. Okay, so then we are considering a transition between this P small and this P large, giving us this formula for the matter power spectrum of modified gravity. Okay, so and this is the performance of our model, considering several models already implemented in some versions of the Boltzmann solver class. In this case, we are considering MG class in high class. So for these several models, we found in general an accuracy of around 1.5%. And this is just a plot showing the agreement of a formula against numerical data. So you can see that the errors, the source of errors are basically due to we are neglecting the typical oscillations in the matter power spectrums due to baryon acoustic oscillations. So, and this is just a plot for a given model, which is this Planck-like model. So we can see here that the fit is excellent indeed. And now we want to move. This is the work I'm trying to finish here in Chile with Domenico. And is that we want to add the wiggles we neglected in previous works. So the first thing to mention is that the wiggling method, which is used in several cosmological analyses, to just extract the smooth part of the matter power spectrum, yeah, to different results. So in this case, we are comparing our formula from genetic algorithms, the Eisenstein-Hu formula, and a filter for signal processing, which is the Savitsky-Golay filter. So indeed, you can see that all three wiggles are different. And so we try to use the physics-inspired approach to machine learning, which is just to add some priors to the formula we are trying to find. In particular, for the problem of the Baryon acoustic oscillations, we we consider that we have a sinusoidal function which represents these Baryon acoustic oscillations, which only occur below the sun horizon. And then due to photon diffusion or silk effect, we have an exponential damping factor around the silk scale. And also we have an amplitude suppression for the sign due to velocity overshoot of baryons. So inspired by the Eisenstein-Hu formula, we found that the transfer function of baryons in the Eisenstein-Hu formula is given by this expression here, which is too complicated again. But for the ranges of the values we are considering for omega B and omega m, we found that these terms, which are the most complicated, are simple fitted by these power law functions. And the silk damping or silk scale is just given by this expression. And this expression here for the sun horizon is given in one of the papers by Isaas and Seris, by one of collaborators. And thus, we want to find a formula similar to TB, but using genetic algorithms. So at the end, the transfer function, the full transfer function, is given by the transfer function with the wiggles, which I showed earlier, and the formula for the wiggles, which is just this sinusoidal function with the oscillations below the sound horizon, an exponential suppression around the silk scale, and a suppression term due to the amount of matter. So we found these simple expressions for the corresponding functions in a formulation, and this is the agreement with numerical data. Okay, so here we are comparing our transfer function with the full Eisenstein-Hu formula with respect to data from class. And you can see here that our formula provides an accuracy below 0.5% for almost all the scales, and just a drop in the accuracy when we have the first peaks of the baryon acoustic oscillation signal. Okay, and the thing with the formula is that highly interpretable. So in the case of Eisenstein-Hu, okay, you can see that all the formulation, the complete formulation requires many terms that indeed they are not all based in physics, because at the end it is a fitting function. But in our case, all the terms we are considering have a specific physical origin. So since the baryon acoustic oscillation signal indeed does not depend too much on other factors like massive neutrinos or modified gravity, which only modify the matter power spectrum at the largest scales. So we can use our formula and add it to the matter transfer function considering massive neutrinos. And this is the accuracy we are obtaining. So you can see here that it is below 1% for the case of massive neutrinos, and in the case of modified gravity, is below also the 1% range, and just a drop in the accuracy for the first peaks in the signal again. So, thank you.
Anyone have any questions? Please. Can you explain a bit the physical origin of those terms in the formula?
The physical origin of?
Yeah. So you said that your formula has all the terms that are there in the physics function, you can see the physics behind it. Can you say a bit about that? The physics behind the stuff?
Well, the physics behind. Okay, so we need a sinusoidal function basically because the Byron acoustic oscillation is due to is induced by pressure in the baryon photon fluid. So it is occurring just.
For example, there's a sign function there, that the physics of that is the BAO.
Yeah.
Like when the other guys do not have the sign function, for example, the Eisenstein.
Eisenstein who? Yeah. Yeah, they also have a sign function, and indeed it is all based on physics. The Eisenstein-Hooke formulation, it is based on physics, but the problem is that it is too complicated because maybe it is too much based in physics. So you can see here, okay, and they have this Bessel function here. Yeah, so the sign function is basically the acoustic signal, which occurs only below the sound horizon. And we have here a function which is just adjusting the first peaks, trying to adjust in the first peaks. And we have after photon diffusion, you know, when the universe is expanding, so you have basically a diffusion from photon from the primordial plasma, and this represents an exponential decay in the amplitude of the matter power spectrum. So we have this photon diffusion effect here, and this term here is just to say that the sign is not going to 1 and -1 and just to a constant value due to this velocity overshoot that baryons are not coupling to photons anymore, but to cold dark matter.
We have a question on Zoom, Daniela.
Yes. Can you hear me?
Yeah, I can hear you. Hi.
Hi, nice to meet you. Thank you for the talk. So I have a question about how do you train your algorithm? Because I wonder if your accuracy is some average accuracy over cosmological parameters, or so can you go into details of how you train your algorithm?
Yeah. Well, okay. To train the algorithm, indeed, what we did is just to compute the transfer function from class for all the range available for K is like 10 to the -3 to 1.6, more or less. considering several pairs of omega B and omega M and omega neutrinos. And
Okay.
yeah, and then we pass this information of K, omega B and omega M, and the transfer function to the genetic algorithm. And the genetic algorithm is trying to find a relation between K, omega B, omega N, and the other parameters to fit the value of TK.
Yeah. Okay. And then, so your accuracy change depending on the parameters that you have, right? It's not homogeneous in parameter space.
No, it's not homogeneous. So thanks for the question. Indeed, that's the reason of this plot here in the right hand side.
Okay, right. Okay, this is for lambda CDM, not modified gravity. Right?
Yeah, this is for lambda CDM.
Okay, and how can we say if 1% is good enough or not? So are you planning to test this with real data just to check that the errors of the prediction given by the machine learning method are under the error budget of the survey or something?
Well, that's a question we have in the modified gravity paper. Sorry.
Okay.
Because the calculations of the sound horizon peak, right, is around 1% for Euclid. So if a formula is reproduced in the numerical calculation or from a Boltzmann solver in a 1% range, so indeed we are in a range of
Below it.
yeah, for the current needs of this kind of service. At least we are there. And we are planning to use real data. Well, it's a work we want to do, but we are planning now. But
And
kind of real data. Yeah, but real data for the matter per spectrum and linear order.
No. The idea is to use one thing that, for instance, we have to mention is the reason why people started to invent hitting formula for the metaphor spectrum. But it's not because it's nice, it's fast, and so on and so forth. But the reason is that when you do correlation function, you're only interested in the position and the height of the peak. You don't care about the rest. So how to do that is that you take your full Boltzmann super amazing code that gives you the truth plots and everything, and then you divide by a smooth power spectrum. Okay? So you're interested only in the oscillations. That a sinus in the Fourier transform of a sinus is a delta function, right? So that's why we have one bigger. It's a little bit people went on and on, just to do okay, well, we did first reason not only for the gravity, just the full power spectrum, just to divide not the original. I mean, just to say, okay, the idea when we use data would be take a full power spectrum from a Boltzmann solver, divided by no wiggle blocks, there's a smooth amplitude, the shape, and see what we get from the BL measurements. Then, so measuring HDA, and then the use, okay, what we have also this one with the BAO, is okay, what happens if we use this one, which seems to look nicer, do we get the same stuff or not? Not because it's easier to, let's say, to have a shape, a little shape, the lower spectrum. It's all you care, okay? Another thing is that you don't know how BAO, the wiggles of the wheel, behave in a different universe, no? Different theory, let's say. So then the comparison would be that. Okay, look, if you use that, then you get the same result as standard procedure. You know? This is the overall idea, and that's what people are trying to do now. And at the end of the day, okay, people will use this is a sort of machine learning, but people now, for instance, are moving towards the emulator stuff, which at the end of the day, it's always a fitting expression of something. No? Emulators that just complicated way of meaning something, you know? But the idea behind is better.
And one of the things of of this kind of formula, of this smooth formula, is that they are used indeed in cosmological analysis. So one of the problems is that we didn't have a formula for modifications of gravity. So indeed we have some emulators for Husavitki, for the very typical models. But the formula intends to reproduce the smooth transfer function for any of the viable modified gravity models. So indeed, we can do this BAO analysis, typical BAO analysis, for example, Planck-Late model or any of these prop2 models in high class.
Okay, thank you. And I have another question. Two more questions, sorry, if I have time. So when you say a physics informed prior, you mean telling the algorithm I prefer to have sinusoidal functions in my results, right?
No,
Okay.
not really. So the thing is that in genetic algorithms, typically we have a random search in the function space. So you tell the code to look for sine, for exponential, for logarithm, and that's it. So in our case, we are doing a simul with Monte Carlo, and thus we are considering priors in the function space of the model. So indeed, the code is looking for this formula, for this exact formula. And we are just saying that we are just telling the code to trying to find this parameter A1, A2, etc. So this is the physics inspired part.
But it's a hyperparameters. How you don't find you tune it.
Yeah, the code fine. The code find these parameters.
Okay, so you don't tune it by hand. It's just hyperparameters for me is something you choose, right? And you use grid or something to find the best one.
Okay, so you said that the hyperparameters you have to tune it.
For example, in neural networks.
Yeah.
You tune the number of neurons, but the parameters that the neural network is finding are the weights, right? So it's different hyperparameter and parameter. That's why I wonder.
Okay, maybe it's a wrong name here. Maybe, yeah. And in this case, these A parameters will be the weights.
Okay. And the last question. I'm just curious because, for example, Domenico, when you do the base ratio between two models, so the idea is also to use this to, for example, compare modified gravity model versus lambda CDM, right? So you can use one emulator for modified gravity, for the transfer function of the modified gravity model, but you have to train a different emulator for lambda CDM, right?
Yeah, is that have it?
Yeah. So yes.
Yeah, okay. Is that correct, right? You have different emulators for different cosmological models. Because the parameter space change. Okay, so then you may have different accuracies for the different models. For example, as you increase the number of model parameters, that might be more difficult for the emulator to perform better than the CDM. So when you do base ratio and you have different accuracies of your emulators, will that change the results of model selection methods?
That will definitely change, yes. Yes, because
so should I trust model selection when I have emulators, different emulators for the different models?
Well, the only thing you can, that's an excellent question, and the answer is I don't know, honestly, but yes, it's true because okay, we increase the prior volumes basically, and then okay, everything will be rejected by the Bayesian ratio.
So one thing to go is just to say, okay, let's fix some of the logical parameters. Let's try to have, let's say, the same numbers. It's okay, the emulators, like in this case, if you want to do some Bayesian ratio, we should allow the change of parameters that you have here, no?
Yeah.
And so yes, everything would be excluded, no, whatever. And modify graphic or very complicated model would be excluded by the ratio. So the thing to go is just to have, to set the same number of parameters. I mean, to fix some parameters for one complicated model and to see what we have. For instance, one way is to say, okay, let's consider not the physical ones like omega n, omega p, but some bias term, no? Yeah, this is something that was discussed in the conference 2 weeks ago, and it was one issue, how to do Bayesian statistics.
Mm,
Yes.
okay, interesting.
I
So
don't know.
future
We don't know. And yes.
future work. Okay.
So in the linear part, they use this technical theory stuff, and they have, I don't know, 5 different biases for the variance, you know? And local, non-local, blah, 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 no? And yes, I mean, you have to fix something.
Okay. Okay, thank you. That's all for my end. Thank you for the talk.
But please, I mean, there's someone work on that, so we need to go ahead on this. I mean, we are stuck with bias. So.
Does anyone have any more questions? Okay, if no further questions, let's thank again to John.